Hello, one. So we are gonna draw a expression, a formula for the continuously compounding interest. So the first of all, we want to remember the compound interest formula we have, and we even know how to get this formula in the first place. But I'm gonna just use this one to make it in compound interesting uh, continuously. Okay. So if we want to find the value of the money after investing, let's say P dollars, like P, like say principal, and the formula that we used was one plus the R over N, right, to the N times T. So like P is the principal, the amount of money you invest, and R is the rate for the annual rate, and then N is the number of times that you are doing this per year, and then T is the number of years. So now we are gonna just play with this, and then at the end we want to get uh, the another like expression, another formula, I'll say. So that will be slightly better looking. Okay, so A will be equal to P times E to the R times T. So this is what we are trying to do. So to do so, like we want to just play with this. Like I'm gonna do first, you know, definition of the E. So let's remember that as well. So the E was the number that we got, the Euler's number. If you take the limit, okay, and goes to infinity, which means if you just choose and as larger numbers, so the expression 1 plus 1 over n to the nth power is equal to our Euler's number. So if you plug like like n equals 1 to 10, 100,000, whatever, which we've done this a bit before. So then this is gonna be getting close to a number that's 2.71 approximately, and then we call that's E. So that's how we get that in the first place. So that's what we are trying to do. So we want to play with this, and then at the end we are going to get this guy, and so we can get this expression. But there is an R right here, but E doesn't have that. So we just need to remove this guy because we have one right here. So one way to remove this R is maybe writing as reciprocal. So P times like 1 times 1 over. So this fraction R over N can be written as N over R. So that would be the same expression as this one. And since I like to get N over R from the denominator, so maybe I should want to get this the same for exponent. So which is why I'll just write this N as N over R, and I'll just multiply this by T, but I cannot just multiply by T because I just introduced R in the exponent, which is why I'm going to multiply this by R times T. Because if I cancel these guys, that should give me N times T, which is what we have now. If you simplify this one, you get R over N. If you simplify this one, you got this one, which means this expression is the same as this one. And you are going to see why I'm doing this in the next step. So that is equal to P. And then, 1 over some fraction. So like, if you want to like choose, let's say this guy, N over R is like a number. So since this is a number, N over R, like N is a number, R is a number, the fraction will be another number as well. But instead of writing fraction, let's make that another variable. So I can just write this guy as 1 plus 1 over H to the, we have the same expression right here. So that is also like H. And then times R times T. But instead of writing times, I'm going to just write this guy as power on power, so exponent properties. So that's is going to be R times T. Okay, so the reason I'm just writing this way because the definition of the Euler like number is 1 plus 1 over N to the N power. When N goes to infinity, that's going to be approaching to that E. So now, like if you choose N, like if your N is going to infinity, which means you are just doing this like compounding infinity many times, then N over R is also approaching to infinity because R is just a percent. So regardless of the value of this, since this goes to infinity, then this fraction goes to infinity as well, which is what we want. So meaning that the R over N over R approaching to infinity, but that is actually N over R was the RH, so which means RH is approaching to infinity, right? So I'll say H is approaching to infinity. Since H is approaching infinity, this is the same thing. No, in our definition, it was N, but there's no difference when you change it to H. So 1 plus 1 over H to the H power, if H is approaching to infinity, then this parenthesis is actually getting our Euler number. So right now we can just say this is going to be equal to P times E to that exponent. So that will be our final answer. As you see, this is what we were trying to do. So the reason why we like this one, because if you do compounding more than like what we used to see, like if you do 10 times, you get a better value. If you do 1,000 times, you get slightly better than that. And if you do this infinite many times per year, then you're gonna actually get the best value of the interest. And that is gonna be our like Euler's numbers when you actually do this continuously, which is interesting. But anyway, so this is the I will say expression that will be used if you are compounding infinitely many times or continuously. So the P will be a principal, E is our Euler number, and R is the rate per year in percent, and then T is the number of years that you are doing this. Okay. So we will do some examples, but that was just the definition.